Sarabhai's life. Actually, his father was an industrialist, but was a very progressive minded. From the very beginning, from the childhood, the upbringing of Sarabhai took place under a different environment. That atmosphere from the Montessori, he studied in the Montessori, and it is a Montessori for a new approach in education system. And he never joined any conventional schools, but he joined a Montessori of where on some experimental basis education at that time was started. His father chose that experimental study for his son, and he is one of the 8 sons. Ambala Sarabhai has 3 sons and 5 daughters. That is 8 children Ambala Sarabhai. Now he started his early career with a Montessori. Then he joined in the Gujarat College, Ahmedabad. He passed from that intermediate from Gujarat College, Ahmedabad. Then 1940 he then he went to Cambridge for his 1940 from St. John's College University, under the Cambridge University, St. John's College, and where he did his graduation, but tripos degree. But at that time, the World War started, he has to return to India. And he has to return to India, and he then joined Indian Institute of Science. He worked under the supervision of C.V. Raman, Professor C.V. Raman. And in 1945, he again returned to Cambridge, and he submitted his PhD thesis on cosmic ray investigation in tropical latitudes. And afterwards, he again came to Indian Institute of Science and joined there. But he soon realized that India is struggling for so many things, for communication, for agricultural sector, for weather sector, everything. And in 1959, Sputnik was launched. Sputnik by Soviet Union. Now he is very much impressed, but he think about the context in the context of India, that India need education, India need its agricultural need to be benefited in its agriculture by space mission, India need better communication in all aspects. He understood that we cannot compete with the developed nation in exploration of space. But the space mission, we have to start. Unless we can start, we will be nowhere in developing a country. It will be a very pitiable situation. And in 1947, he took the challenge for developing the laboratory for science also. In 1947, he established PRL, Physical Research Laboratory in Ahmedabad, and also Ahmedabad's Textile Industry Research Center in a research association in Ahmedabad. On the other hand, it is a textile research, is a business-oriented research, and on the other hand, PRL, the Physical Research Laboratory, for the first laboratory, state-aided laboratory in India, a big, large-scale laboratory. And through whole of the life, he established so many centers like Indian Institute of Management, Ahmedabad, the first rocket launching station at Thumba, the Nehru, in 1965, he founded Nehru Foundation for Development with focus on current problems in society and individual in particular. In 1966, he established Vikram Ambala Sarabhai Community Science Center to promote science and mathematics amongst students and public in general. He also established the experimental scientific communication art station, and which is then transformed to Space Application Center. He also helped to establish the Electronics Corporation of India in 1967 and the Uranium Corporation of India. And also the major contribution also his ISRO, establishment of ISRO, Indian Space Research Organization. And he died in 1971. And within that small period, he established so many organizations. His wife is Mrinalini Devi, was a classical dancer. And with help of Mrinalini Devi, he also established a dance academy, Darpana Academy of Performing Arts. He has also interest in literature also. He established Darpana Academy of Performing Arts in Ahmedabad with Mrinalini Devi. And how a person like that is diversified field. A person contributed in diversified field. And we know, if we come to, interestingly, we come to know that there is a big cultural background and contact with so many influential persons at that time. There is some family contact. They are influential in political and cultural environment also, like Rabindranath Tagore, Maulana Abul Kalam Azad, Sarojini Naidu, C.F. Andrews, C.V. Raman, and mainly Mahatma Gandhi. He took lesson from all that in her very childhood, and from this he developed a rich acquired a rich background in literature, in politics, and the critical sense and deep sense about the society, how society can be developed. Now, Vikram Sarabhai in 1969 in a TV interview talked about his family. My father was very unconventional. My father did many things for which he was thrown out of the caste, and the influence of Gandhi on my family was very strong indeed. So that although my childhood, at least I was, through my childhood, at least I was brought up on doing what one left right rather than what necessarily society thought was appropriate. And this is the statement by Vikram Sarabhai about his father. And when he talked about the space program, he said, we do not have the fantasy of competing with economically advanced nation in the exploration of moon or the planets or manned space flight. But we are convinced that if we are to play a meaningful role nationally and the community of nation, we must be second to none in the application of advanced technology to real problems of man and society. And these are the visions of Vikram Sarabhai, from where we can understand that the man, what type of man he was. Also, so many awards also he received. This is nothing special about such a big person. He received Padma Bhushan in 1966, Padma Vibhushan in 1972, and the lander, we know that lander of Chandrayaan-2 was named after him, Vikram lander. And there is a crater, more interesting, there is a crater on moon which is named after him, Sarabhai crater. And it is 8 kilometers in diameter, and its coordinate is 24.7 north and 21 north east. And in 2019, ISRO announced Vikram Sarabhai Journalism Award in Space Technology and Research, a cash prize of 5 lakh and memento, and it was announced by ISRO in 2019. And he was chairman of Atomic Energy Commission, and so many distinguished chairs he was placed. But these are the short life history of Vikram Sarabhai. It requires more than an hour to everything if it is not a place to elaborate, because we have to constrain in time. Hence, with that, very few words, and with regards and homage to our respectable scientist who contributed so much for the development of our nation, we feel proud of him. And with that few words, I convey my heartiest gratitude in the memory of Dr. Sarabhai, and over to Tamal for next session.
Thank you, Arindam sir, for giving such a nice overview about the different works done by Professor Vikram Sarabhai. Now I will request Biplab Vijay to start his talk. Title of his talk is A Search for Pulsar with uGMRT. Okay. And Biplab Vijay is currently NCRAS PDF student, and he is an PhD student of ours. Now it is over to Vijay to start the talk. Vijay, please share.
Okay, good evening to all of you. Today I am going to discuss some techniques by which we usually search pulsars with different radio observatories. I would like to say that, okay, this is just, in this session, I am going to just discuss about the techniques which are being used here. So the thing is, pulsars are actually rotating neutron stars, and that emits radiations in almost all the frequencies. And it is easy to detect in radio frequency. That is why radio telescopes are used in order to find out new pulsars. Now, when we do a blind search, that means we do not know whether in a part of the sky there is a pulsar is present or not. We usually take radio data from that part of the sky, and then search that data in different parameters. And those parameters are DM, that is dispersion measure, period, and sometimes also we use period derivatives. So for that, actually, we have to know the data structure. Most of the pulsar data are actually 3D data sets in time, frequency, and intensity. Then also we have to know whether radio frequency interference or RFI are there or not nearby. If it is there, if it is a RFI zone, then we have to remove those RFIs. Then we use certain techniques like de-dispersion plan, and then de-disperse it, and then we do a harmonic search. I'm going to explain all of this thing one by one. And after that, we do a Fourier transform, and then we select some of the pulsar-like candidates, and then we check whether that is a real pulsar or not. So first, as we know that pulsars are rotating neutron stars, and it emits in all the frequencies. So because of this rotation, when the emission comes into our line of sight, we see the pulsar, and when it goes away, we don't. So it's just like a lighthouse. So the period of rotation is equivalent to the period of the pulsar, and it varies from 1 millisecond to around 10 seconds. So if we take a radio telescope and focus it on a pulsar, then we will see that periodic signal. We are getting periodic signals in frequency and time, which can be seen here, that it's a time series, and we are getting peaks like this. These peaks are actually when the pulsar, the emission of the pulsar comes into our line of sight. Now, this is only a single time series at a particular frequency. Now, as we know that pulsars emit in a wide range of frequency, then it won't be something like that. The data structure would be something different. It will be a three-dimensional data in which in x-axis we have time, in y-axis we have frequency, and in z-axis we have intensity. That we are going to see in later on. Now, when we get something like this, a time series versus intensity plot, so for a strong pulsars, we can easily see the peaks here, and we can identify that, okay, this is a pulsar. But for a weak pulsar, the time series will look like something like this. And it is very difficult to identify a pulsed signal in this kind of time series. So what we do is, if we know the period of the pulsar, we start folding it one by one, which is pictorially represented here. So we fold it one by one. So what happens is, when we fold it like this, the noise will decrease with square root n times, resulting a sharp signal which will look like this. And we plot it in intensity versus phase of the pulsar. But this is for a one-dimensional data. Now, if it is a two-dimensional data, it will look like something like this. So here, in y-axis, it is frequency. In x-axis, it is phase, and then folded individually in all the frequency channels. So individually, we will get something like this. This is for a typical pulsar, which is emitting in all the frequency range, but we have only selected this frequency band. We should get something like this, but in reality, we get pulses like something like this. Now here it is frequency, and here it is time. Now what happens is, because of the electrons present, interstellar electrons present, the pulses will, the radio signal will get scattered, which is called as dispersion, and because of which lower frequency signals will come at a later stage, whereas higher frequency signal will come at an earlier stage. So the measure of this is called as DM, which is nothing but the integration of number of electrons with, that is in the direction of the pulsar, with integrated over the distance of the pulsars from the observatory, and that is what we called as DM. So a pulsar DM always and must lie in between 0 to somewhat like 1200. Now, if we do not correct this dispersion, then we will get this kind of broad signal, and again it will be difficult for us to identify it. But if we correct for this dispersion, then we will get a peak signal. It is because the delay of the pulsar signal to reach the observatory, and this delay can be represented by this equation. So for a known pulsar, since we know the distance, thereby we know the DM as well as we know the period, it is very easy to fold that pulsar with that after correcting it for the particular TM. But if it is an unknown pulsar, then what can we do? So that is where these search techniques are used. So since we do not know the DM and the period of the pulsars, our search parameters will be basically DM and period. So for that, what we have to do is, we have to first consider a range of the DM. Suppose from DM1 to DM600 or something like that, say 800, something like that. Now we divide this range into several DMs. and with certain DM steps. Then we use correction method for this individual DM, so that we de-disperse it with that particular DM, and then crunch it in frequency, so that we get only a time series, just like this time series for individual DM. And after that, what we do is we use a Fourier transformation for that. Since it is a periodic signal, in Fourier domain, we will see a single peak at a particular frequency, and that frequency is corresponding to the period of the pulsar. So if our if our DM is correct, if our search DM is correct, then we will see this kind of a peak in the frequency domain. And once we get this peak corresponding to this frequency, we take the period and then fold the data. And after folding the data, we see whether we are getting a folded profile or something like this or not, or something like this or not. Now, if we get that, then probably it is a pulsar, and we re-observe that and to see whether we are getting the same thing again or not. Now, if it is not a pulsar, we won't be able to reproduce that data. So first thing what we do is we take several trial DMs ranging from 0 to 800. Then we de-dispersed at each DM and then crunch the data in our frequency to get a single time series. Then we do the Fourier transform to see whether we are getting a peak, we are getting a signal at a particular frequency or not. And then corresponding to that frequency, we find out the folding period and then fold it. So this is the basic technique. But then again, sometimes what happens, there are RFIs, just like power line, just like if there is a spark or not, they also can produce this kind of thing. Not only that, if we look this diagram correctly, now this is not a dispersed, this is not a de-dispersed data. Then we will get something like this. But if we de-disperse it in a wrong DM, this oblique line may become something like this here, unless we de-disperse it in a correct way. So a pulsar can be detected in several DM. So what we do is we plot that DM and SNR of this thing, SNR of this pulsar in FFT domain to see at which DM we are getting the highest DM. So a DM versus SNR plot can be seen like this. So for a true pulsar, it appears like a bell curve. So at a particular DM, we will get the highest SNR. So we choose that DM as a particular, as the DM of the pulsar. And then we take this frequency, and corresponding to that frequency, we find out the period and then fold it. Now, if it is not a true pulsar, if it is a RFI, or if it is because of some other effects, then we won't get this bell-shaped curve. We will get something like this. This doesn't have any kind of shape or etc. So whenever we get this kind of thing, we directly reject it, saying that okay, this is not a pulsar, this is an RFI. We only choose this kind of thing and then do the foldings, and find out whether it's a true pulsar or not. So now, what are the softwares we use for pulsars, or to search for pulsars? One of that software is called as PrepFold. So as you can see in this diagram, this is frequency versus the phase diagram. That means it is already folded in time. And this is time versus phase diagram. That means it is already folded. It is already folded in the frequency. Now, after searching the DM, after searching it in Fourier domain, and then after plotting this diagram, we find out the corrected DM, and then de-disperse it, and then folded it, and it was found out to be the DM was found out to be 69, and the period of the pulsar is found out to be 442 DM. So this is one of the software that is called as PrepFold. Now, what happens if we have large number of RFIs, just like power line, etc. Now, RFIs are mainly due to terrestrial structures like TV stations, or like maybe somewhere there is a spark, or maybe because of some machine or some rice mill, etc. is running. Since they are terrestrial, the sources of RFIs are terrestrial, its DM must be 0. So what we do is, from the data, we de-disperse the data at 0 DM, then subtract that data from the original data. So that actually remove almost all the DM, almost all the RFIs. So once it is removed, so the data will become clean, and then we follow this kind of procedures. Now, for single disk antennas, it is easier to detect. It is easier to handle a single disk antenna, as the single large disk antennas are only meant for pulsar search. But if we have an array of antenna, for searching purpose, we use two methods: incoherent array method, and another is phased array method. Now, incoherent array method is used for searching of pulsars, for blind searches of pulsars where we do not know anything about the pulsars. And phased array mode is used for targeted search, that if we know, okay, there is a pulsar is there at a particular point, somehow you know, then we will search it. We will just focus the antenna there and use phased array mode. Now, incoherent array mode means we get the time series data, which is time versus voltage. We square it and then add it for all the antennas. That is what we call incoherent array mode. And then we perform all this. All these methods. Now, the important thing for a blind search is selection of the sky area. Now, how do we select the area of the sky? We take different areas of the sky, run a simulation based on our telescope configuration, and see that if we run a blind survey, how many pulsars we may get. So using that method, we selected a sky area something like this, from 9 degree L to 30 degree and 5 degree B to 20 degree. And we choose 100 hours of observations at in that area. And by running that, after running that, we analyze the data. And for analysis of the data, we used a software that is called as SIGPROC. First, we remove the RFI using GP tool, which I think I will explain in detail in my next presentation. And then we create a de-dispersion plan, as I have mentioned, that we select a DM ranging from 1 to some certain DM, say 800, and then divided that with certain DM steps. So we will get like 1000 or 1500 DMs. Then we de-disperse them at that data at that particular DM. And then we crunch it in frequency to get a time series. Then we do the FFT. And from that FFT, we see whether there is some peaks present in there or not. If it is there, corresponding to that frequency, we select. And then we fold the data to see whether we can see a pulsars or not. So using that, actually we found 8 new pulsars till now in our data. Still more than 40% data are there to be analyzed. We have out of which we have confirmed 4 of them at different fields. Now this is just to find this is just for the search of the pulsars. Now once the pulsar we find, then we need to locate that pulsar. Now how to locate that pulsar? Now suppose we have 4 different fields, nearby fields, and we found that pulsar in this nearby 4 different fields. Then what we do is we make images for these 4 different fields to see what are the point-like sources present in that image. Now, also, if the pulsar is closest to one of the field, the SNR of that pulse will be higher there. For example, this new PSR is present in these 4 fields where the SNR of the pulse is higher in this field. So we made an image something like this. Now, these are the 4 fields where we found the pulsars, where we found that particular pulsar, where we have detected the particular pulsars, and its signal to noise ratio is higher here. So we choose all the points that is nearer to the 613D. So these are the 11 points we choose depending on the SNR of that pulsar, and then we do a PA beam search on this. That means we focus on our telescope on these 11 points. We found out that, so doing that, we found out that at a particular point, that is S11, the signal to noise ratio of that pulsar is very high. So that means this is the true location of the pulsars. We then find out the array and deck of this point, and that is our true location of the pulsars. So as you can see, that new pulsar has the highest signal to noise ratio and this nice profiles, etc. here. So this is the true location of the pulsars. Now, once we know the location of the pulsar, then the next thing is actually we have to time that pulsar to find out different parameters. Parameters like its period corrected up to several decimal places, its DM, its period derivative, and also its array and deck that is corrected up to several decimal places. To do that, we use a method that is called as timing, which I'm going to actually discuss in one of my presentation later on in detail. Similarly, actually, just to show this, so this is one of the timing curve where we have to plot actually the date of observation and actually the date of observation and the periods, and then we fit it. Once we get a good fit, we then get the perfect period, the period derivative, even the magnetic field, etc. All these things. So in that way, actually, we found we found 8 such new pulsars. And the next step would be to find out this. It's actually what you called as its power index. What is the power index of this pulsar? So that's again a long story. So long story short, actually, we have found several such pulsar. Now, these are some of the interesting candidates which were confirmed using our observation. And some of them are like 4 millisecond, 3 millisecond pulsars, which we have found right now. So that's all. This much. So thank you.
Thank you, Biplab. Now the talk is open for discussion. If you have any questions, okay, you can ask in the chat box, or you can unmute yourself and ask. Now already we have some questions. Okay, Biplab, please look into the chat box.
There are some questions. The first question is, what is Presto? Okay, Presto is a software that is used in basically used for folding purpose. Now this Presto also does one thing. What it does is actually it can be used for searching for the pulsars. All the steps what I have said, creating a de-dispersion plan, then de-dispersing it in several trial DMs, then doing the FFT, and then getting the frequency, and then folding it with that frequency. All these things can be done using Presto, but we have to again tweak it a little bit. I mean, this software is only used for folding purpose, nothing else. Okay, how we generally name a new pulsar? Depending on the array and deck of the pulsar. For example, a pulsar has an array of 18 degree, 32 minute and some second, and then the deck is something like that. So what we will do is we use the fast for characters of that pulsar. For example, J1838 minus 1212 has an array of 18 is to 32, and deck is 18 is to 18, minus 18 is to 18, something like that. What is the main cause of dispersion of the pulse signal that coming from pulsars? Is it for interstellar medium? Yes, it is for interstellar medium. It is like, I mean, the signal with lower frequency, they get scattered by these electrons present in the interstellar medium, because of which actually it get delayed. It is just like, you can say, I mean, normal dispersion we found in the in optical range. Just when a white light pass through a prism for different wavelengths, the refractive index will be different. So it is just similar way. That is because it is because of which actually the lower frequency signal will come at a later stage, and the higher frequency signal will come at an earlier stage. And because of which actually we did disperse it. As you mentioned, sources of array is mostly this. Yeah, DM is, as I have mentioned, DM is actually, I mean, the electron column density that is present between your observatory and the pulsar. It is measured in mainly parsec per centimeter cube. Now for terrestrial signal, there it will be obviously 0, because it is just present in few kilometers away or something like that. So if you just convert it into parsec or something like that, it will be almost 0.00000 something like that, 10, 15 zeros like that. So we can easily take it as a 0. Do these new reported MSPs exhibit any new features which didn't show other MSPs? No, most of them exhibit the same features. Just for one new pulsar, actually, it is interesting to say that, okay, that pulsar is seen in some days we could see that pulsar, and in some days we could not see that pulsar. That means either on those particular days, the direction of that, I mean, in those particular days, there is scintillation or something like that, because of which the intensity of the pulsar falls, or it may be because of some other reason we do not know. And second thing is, are they galactic or extragalactic pulsars? All these pulsars which we have discovered here, all these 8 pulsars, all of them are galactic. If the DM of the pulsar goes beyond 200, then we can say that it's extragalactic. But most of the pulsars we have detected is the DM is within 100. So all of them are galactic pulsars.
Any other questions? You can also unmute yourself and ask question to Biplab. I think there is no question.
Okay, before ending, I have to have some comments on this today's very important event is there, because 2nd August is the birth centenary of Prafulla Chandra Rai, Professor Prafulla Chandra Rai, the great Indian chemist, Bengali chemist, industrialist, and was also the discoverer of mercurium nitrate, mercurium nitrite. And we all should feel proud of him. And the great son of Bengal, he contributed so much in mercury chemistry, in sulfur chemistry. And the he was pioneer in this field, and he also established Bengal Chemical. Okay, and with that few note, with homage and with best regards to that Bengali chemist, I close my comment.